All right, yeah, so we like Infinite Craft. We've been playing this for the past 2 months. It's a wonderful viral browser game that kind of took the internet by storm over the last 2 months. So this is what it looks like. It was made by the wonderful Neil Agarwal, who has made a number of other fun internet games. And you begin with this wonderful infinite grid and 4 elements at your disposal. Now, you are going to take 2 elements, say water and fire, and you put them together, and you get steam, as what would happen when you put water and fire together. But unlike other alchemy games you might have seen in your childhood, this is not driven by some creator of the game. It was actually invented by an AI. So all of the outputs in this game that Neil created are derived by asking Llama 2, what do you get when you put water and fire together, or something like that. And this leads to some very interesting combinations you can make. For example, the steam Rex, the car company Saturn, and a fire plant. What happens when you get a Venus flytrap and fireworks?
We aren't sure what that one is either.
Yeah, we have no clue. You can start assembling more complex webs of elements, such as Ant-Man, Legolas, Sharknado, the Antichrist, Sandwich Tiki, Capitalist Zombie, and 50-odd other things. If you put them together in a very specific order, you get Murdon, Christ, Ant Be, Don, Whip It Good. And so, being able to do this, we have to ask, can we craft all the things? If we can craft Murdon, Christ, Ant Be, Don, Whip It Good, can we make everything? No, we can't, but we did try. So we ended up using the power of robots to search 1.8 million combinations of elements. Some of them were sensible, some of them were super lazy, most of them are nonsense, and some of them are a bit concerning cultural biases. 240,000 distinct elements were found within our data set. Some of them are really long, some of them aren't even ASCII. A lot of them are just numbers, just straight up numbers. And a few times the AI forgot its prompt and just told us about Baoji.
So here's sort of our search space here. You can kind of see that we've searched a lot of shorter element lengths and a bunch of, these are all numbers here. But so we ran a bunch of searches, basically doing whatever we wanted, and filled in various parts of this graph very poorly. Notice that PyPlot didn't give us 10 to the 0. I'm very grateful. So an audience participation lightning round. I do want very quick participation from you all. Poland plus city, any guesses? Got it. Great Poland job. Plus food. Great. England plus city. London. England plus food.
Fish and chips.
Brazil. United States plus city.
Pittsburgh.
Yeah. United States plus food. Saudi Arabia plus city.
Mecca.
Saudi Arabia plus food.
Cuban.
India plus city. India plus food. All right, Jordan plus, let's show it together. Jordan plus food. Anybody get Michael? Turkey plus city. We tried so hard to find the better spelling, but we couldn't find it, so you're going to have to live with this. Turkey plus city. Any guesses? Turkey plus food? Turkey. No. Egypt plus city. Egypt plus food? Pyramid. Yeah, it's also pyramid. Okay, so we have this binary operation. Let's do some math on it. It's not associative, so it's really annoying to work with. It is commutative, which is nice. We found some minimal generating sets. One of them is on our shirts. You can just use Win to generate everything. Kind of fun. This is our proof with a very limited number of words. You can efficiently search for closed subsets and familiar algebraic structures, and check the paper. So here's an example of a monoid that we found. It looks like this. We didn't come across, I don't know about the algebra classes here, but we didn't come across this one in any algebra class that I took. So we have a conclusion. All right.
Yeah, so how do we actually find the ways to get all these elements? Clearly we got them somehow through our search, and we want to find the shortest way to make them just from starting out the game with nothing. All right, so if we searched everything more systematically, this would be done for us, right, if we just iterated along the way. But 1.8 million recipes only gets you to depth 4 because of the power of exponents. So this is why we searched in all kinds of random ways to get fun stuff that we can tell you guys. So if we want to find derivations, we actually have to appeal to a hypergraph shortest path problem. This is hard and slow, and the more we tried to make it smarter, it got slower. So we made a compromise by making wrong assumptions about optimal substructure in our problem. We did lots of analyses on this data. We'll show you some examples now. Here's an attempted rendering of our graph. Here's another one. Here's yet another one.
And so from these, we derive this theorem.
We don't even know what this one is.
Yeah. So we figure every research project has a graph like this. And if you want to play with it a little bit, we have a little bit of time. No, we don't. But we have the example derivations. Check out the website. You can look at like how to get, for example, Carnegie Mellon University. You can plug this into Infinite Craft, match the things together, get this. There's some really fun ones here. Here's an example of Dig Dug 63, which is it likes to count. Okay, it really likes to count, but notice that it's really counting poorly. But okay, that's great. Steampunk Will Smith, anyone? Here's another number. I don't know why you have to go through America plus tornado is Trump, but... Oh, and one of my favorite things that I would do is it would really latch on to one concept and just add it to everything. So here's Sharknado, but like with everything. We have some... So most of these aren't even funny, but you know, here we are. So yeah, check out the website, check out our paper. We're done.
All right, everyone, the moment you've been waiting